Hello everyone, today we're finally starting some combo, and we're doing two intermediate combinatorics problems today. Also, I'm actually going to add one number theory problem because I realized that this is a problem I did earlier that I haven't did a video over yet. Anyways, we're starting with this one. We have two convex polygons and they're drawing on the same plane, and we're trying to find how many intersections there are maximum. And n1 is the number of sides of the smaller polygon, and 2 is the number of sides of the bigger polygon. And we're trying to find the relationship between number of sides and maximum number of intersections. So you can pause video or think about it yourself. So anyways, we can think about it this way. For the smaller polygon, let's consider one angle, the smaller polygon. This angle can be intersected at most twice, because if you think about it, say the other polygon is red, the only way to intersect them more than twice is if we go in again. However, if we go in, we have to come out again, which means that we intersect it either once on the top, twice by going through, or 4 times by going across and then in, then out. Unless, well, of course, do a tangent, but that obviously is a curve, which is not possible since we're considering convex polygons. So if we don't consider the case of a curve, it has to be a zigzag shape for it to intersect one edge more than twice, which means every vertex can be intersected at most twice. Since the number of vertex is equal to the number of edges, every edge can be intersected at most twice, even though that's actually not true, but you get the idea. So it's just the number of edges times 2, because every vertex, which is equal to the number of edges, can be intersected twice, so it's 2 times the number of vertex, or 2 times the number of edge, which is A. Yep, it's A. And the second problem, I would say, is the little bit more interesting one. We have n people who exactly know one piece of information each, and all np's are different. So every time a person A calls a person B, A tells B everything that A knows, while B doesn't tell A anything. So we're trying to find the minimum number of phone calls between pairs of people needed for everyone to know everything. And we have to prove that the answer is a minimum. So there is a very useful theory, I'd say, in combinatorics that can help us solve this problem. So first of all, let's say we have m people. So this very useful trick or technique is that there has to be a first to everything. So in this case, there has to be a first person to know everything. And let's call this first person this guy. Let's just call him X, right? Because we have to make the phone calls one by one. So there has to be the first person to know everything, and then everyone else can start knowing everything. So what's the minimum number of calls needed to create this person X? Well, X initially only know one piece of information, so he needs every other person to at least make one phone call to him to deliver their piece of information to X. And obviously, there's no other faster way to achieve this, because every n-1 person has to make a phone call. Otherwise, their piece of information cannot be delivered to anyone else. So we need n-1 phone calls for X to even exist. And now that we have an X, how many more phone calls do we need for everyone else to know everything? We'll notice that for any person who's not X calling Y to know everything, we need at least one phone call to Y. And since we're going to need at least one anyways, why don't we just have X call them? So we have to make X make another n-1 phone calls. So we have n-1 that created the X plus another n-1 that X makes to everyone else. So a total of 2n-2 phone calls needs to be made. And we can see that this is obviously possible by just doing the process that we said above. And we can also realize that it is, in fact, the minimum number of phone calls we have to make, because both of these two processes are essential and it is the minimum number. So those are the two combo problems for today. And then we're doing one more number theory because, well, we just need to. Yep. So we have 2 to the 2x minus 3 to the 2y equals 55, and we're trying to find the number of solutions where x and y are both integers. Well, and if the equation's in this form, then it's rather difficult to solve it. However, notice that 2x and 2y implies they're both even numbers, which means that we can actually apply the difference of squares to them, because 2 to the 2x is basically just 2 to the x squared, and then 2 to the 2y is just 3 to the 2y is just 3 to the y squared. So obviously, let me pull up my VS Code. All right. So now that we have this minus, we can just apply a difference of squares. So we have 2 to the x minus 3 to the y times 2 to the x plus 3 to the y equals 55. So obviously now, since it's number theory, we just prime factorize 55, and then we solve an equation, and then realize that there's only one pair of valid solutions. So the answer is 1, which is B. Yep, it's B. Right, we just solve a system of equations from there, which is obviously easy because 55 can only be 155 or 511. So yeah, so that's it for the problems for today. It's 3 pretty short problems, except I guess the second one's probably the most interesting because we applied a very, I'd say it's a pretty neat trick of knowing that there has to be a first to everything. So yeah, the grind report for today. Yeah, I kind of locked in and I got a little bit addicted to number theory, so I did quite a few number theory problems today and nothing else. And yeah, this is my problem list so far. As you can see, prior to September 20th, I've been just mocking a lot, and then my friend told me it's not effective, so I started doing problems. Yeah. Okay, thank you for watching, and I'll see you tomorrow.